In the previous video, we looked at the unit circle definitions of sine, cos, and tan by drawing this picture here. And then we used that unit circle to plot the graphs of sine theta and cos theta, which we've got down here. And we looked at some of its properties and symmetries. In this video, we're going to move on to draw the tan graph and then also look at its properties as well. But what we looked at last time was that tan theta is this opposite side over adjacent side, which gives us, first of all, sine theta over cos theta, which is one method we can use to get the value of tan. But it's also the gradient of the hypotenuse. So if we raise our angle up round here, we can plot the gradient function by looking at the hypotenuse as we go round. So let's have a look at what we've got over here. So starting it back at 0 again. So clearly at 0 degrees, you've got a horizontal ray, which gives you a gradient of 0. So tan of 0 is 0. And then as we increase the angle, the gradient is going to increase. Then when we're halfway through this quadrant at 45 degrees, then the gradient is going to be 1 because the opposite and adjacent will be the same. So we're at 1 here at 45 degrees. It's then going to continue higher and higher and higher until we get to pretty much infinity, just before we reach 90 degrees. However, at 90 degrees itself, our gradient is actually undefined. Okay, there's no value of the gradient at that point because the rise would be 1, but the run is 0, and you can't divide 1 by 0. However, as you continue past 90, we can then jump ahead, and that's going to give me a very, very steep negative gradient, which is down towards minus infinity. It's then going to get gradually shallower, which means that the graph will get bigger in the negatives until we get to 0 degrees here. Sorry, gradient of 0 at 180 degrees, which puts me at this point in the graph. When we go past 180 degrees, we've now got a positive gradient for our hypotenuse, so our graph's going to be positive. It's going to get gradually steeper, doing the same as it did in the first quadrant, you'll notice, until again at 270 degrees, we've got another undefined gradient, another 1 over 0 here, or maybe minus 1 over 0. But then past 270, we've now got steep negative gradients. It's going to continue to get more shallow until we get all the way back up to 0 again. Okay, so this part in blue, this is my drawing of the tangent function. I'll put that on my picture over here. So it's going to do this. It's going to go getting bigger like this, up to infinity. Asymptote here at 90 degrees. It then becomes very negative, climbing towards 0, and then goes up to infinity again at 270. And then it's going to go up from minus infinity up towards 0 again like this. Okay, so that's a rough sketch of my graph there. Okay, so obviously it's the odd one out of the three. It's got the kind of strangest look of all three graphs, but in some ways it's got much nicer properties. So firstly, I want to look at what the period of this function is, because that's what the thing that distinguishes it from these two. The period this time is the time it takes to do this sweep here from minus infinity to infinity, which is a gap of 180 degrees. So that means that tan of theta plus 180, or indeed minus 180, is the same as tan theta. Okay, let's look at the roots as well. It's got roots at, looks like clean multiples of 180 degrees. So I'm writing that as 180 degrees times n, n's an integer. I'm going to use set notation this time to say that n belongs to the set of integers. Then it doesn't actually have any maxima or minima this time, okay? And that's because it goes off to plus and minus infinity. So there isn't a clear finite maximum or minimum value here that we can kind of refer to. But we've got these asymptotes, we can describe those. And those are going to be at odd multiples of 90 degrees here. So 90 degrees and then 180 degrees spaced apart either side of that. So I'm going to write 90 degrees plus multiples of 180, like that. Okay, in terms of the value of tan theta that we can have as a range, tan theta can in fact be any value that we like. Okay, whereas sine and cos were trapped between -1 and 1, it turns out tan theta can be any value as long as you pick a suitable angle. So any real value. That's what I mean by this notation here. Okay, then when it comes to reflecting from positive to negative for our angle, we should think about what happens when we go backwards. So it's going to be something like this. And then if I take a positive angle theta and I reflect it over to negative theta, then just like when we had for sine theta, the values of tan are going to be opposite sine to each other. So that value there for tan of theta is going to be, it will turn out the negative of what it is for minus theta. Okay, the drawing there isn't particularly good, but what's going to happen is negative angles will give you the negative value of tan. So it turns out that tan is just like sine, it's an odd function. Okay, that means that tan is an odd function. Okay, and that is the graph of tan. Hopefully this is all still recap work, and some bits are maybe new as to talking about these things, but hopefully that gets you up to speed with the values of the graph.